This is part one of Phobos. We start with the key question. Phobos, overview and origin. Phobos is one of the strangest objects in the solar system. It orbits closer to its planet than any other known moon, and nobody is entirely sure where it came from. This is episode 1 of our Phobos series. We're starting at the beginning, what Phobos actually is, how it got there, and why that question still doesn't have a clean answer. That last part matters more than it might seem, because the origin of Phobos shapes everything else about it, including its future. We'll get to the implications shortly. But first, let's set the scene. Mars sits roughly 228 million kilometers from the Sun on average. It has 2 moons, Phobos and Deimos. Both are small, both are dark. Both were discovered in the same week in August 1877 by the American astronomer Asaph Hall, who very nearly gave up the search the night before he found them. His wife reportedly encouraged him to keep going. 2 days later, he'd found both moons. A nice story. But the moons themselves raise harder questions. Phobos is the inner one, roughly 27 kilometers at its longest point, about 18 at its shortest. It's not a sphere. It's lumpy and irregular, shaped more like a battered potato than anything you'd expect to find in a planetary orbit. The surface is covered in craters, grooves, and a thick layer of loose, powdery regolith. The largest crater is called Stickney, named after Hall's wife, Chloe Angeline Stickney Hall. It's about 9 kilometers across, which is enormous, relative to the moon's total size. The impact that created it came close to shattering Phobos entirely. Surface gravity is almost nothing, around 0.0057 meters per second squared. Less than 1,000th of what you'd feel on Earth. Drop a rock on Phobos, and it takes about a minute to hit the ground. Jump with any real effort, and you'd leave the surface entirely. Temperature swings wildly too. The sunlit side can reach around -4 degrees Celsius. The night side drops to roughly -112. There's no atmosphere to buffer any of that. Phobos is essentially exposed rock and dust in open space, despite being a moon of a planet. Now, the orbit. This is where things get genuinely interesting, and it leads directly to one of the biggest open questions about this object. Phobos orbits Mars at an average distance of just 9,377 kilometers from the planet's center. That's less than 2.5 times the radius of Mars itself. Extraordinarily close, closer than any other known moon orbits its parent planet. The orbit is nearly circular and aligned almost exactly with Mars's equator. Here's the open loop. That orbit is so close and so tidy that it doesn't fit easily with the leading theories of how Phobos formed. We'll come back to that. The orbital period is 7 hours and 39 minutes. Phobos completes more than 3 full orbits every single Martian day. Standing on the Martian surface, you'd watch it rise in the west, arc across the sky, and set in the east in well under 6 hours. It moves faster than Mars rotates. That's rare. Like our own moon, Phobos is tidally locked. The same face always points toward Mars. So, where did it come from? The honest answer is, we still don't know for certain. 3 main hypotheses have been worked over the years. The first is capture. The idea is that Phobos was originally an asteroid, perhaps from the outer main belt, perhaps a trans-Neptunian object, that wandered too close to Mars and got trapped by its gravity. This would explain why Phobos looks so much like a D-type asteroid. It's dark, with a low albedo of around 0.07, meaning it reflects only about 7% of the light that hits it. Its spectral signature has some similarities to carbonaceous chondrite material. The problem is that gravitational capture is extremely difficult, without some mechanism to bleed off velocity. You can't simply fly past a planet and end up in a stable orbit. Something has to slow you down. Proposals include atmospheric drag from an early, denser Martian atmosphere, or gravitational interactions with other bodies. Neither works cleanly. The maths is hard to make add up, and the resulting orbit would likely be more elongated and more inclined than what we actually observe. The second idea is that Phobos formed in place, accreting from material already in orbit around Mars during or shortly after the planet formed, sometimes called the co-formation model. The difficulty here is that Phobos orbits inside what's known as the Roche limit for low-density bodies. The distance at which tidal forces from Mars would tend to pull material apart rather than allow it to clump together, forming a stable moon that close is not straightforward. The third hypothesis, and currently one of the more favored ones, is formation from impact debris. A large object strikes Mars, throws a disk of material into orbit, and that material gradually coalesces into moons, broadly similar to how Earth's moon is thought to have formed. This model handles the near-equatorial, near-circular orbit reasonably well. Where it struggles is composition. The surface of Phobos doesn't look much like Martian rock. That brings us to the composition problem, which is the knot at the center of all of this. Spectrally, Phobos resembles a D-type asteroid, but it doesn't resemble Mars. If it formed from Martian material, you'd expect some geochemical similarity. If it was captured from the outer solar system, you would expect hydrated minerals or certain organic signatures, and those haven't been clearly confirmed. The spectral data is genuinely ambiguous. Different instruments, different observation geometries, slightly different readings. It could suggest hydrated silicates. It could suggest something drier. Scientists aren't in agreement. This is precisely why a sample return mission would be so valuable. Japan's Martian Moons Exploration Mission, MMX, launched in September 2024, and is designed to land on Phobos, collect samples, and return them to Earth around 2031. Physical samples could resolve the origin question in a way that remote sensing simply cannot. We'll cover MMX in more detail later in this series. For now, the fact that it exists tells you something important. Scientists consider the question open enough to be worth $1 billion answer. Let's close that open loop from earlier, the one about the orbit. The orbit of Phobos is decaying. Not speculation, it's been measured. Phobos is spiraling inward at roughly 1.8 centimeters per year. The cause is tidal interaction with Mars. Because Phobos orbits faster than Mars rotates, the tidal bulge it raises on Mars actually pulls it slightly forward and downward, rather than outward, as happens with our own moon. Phobos is gradually losing orbital energy and edging closer. At the current rate, it will either break apart or collide with Mars in approximately 30 to 50 million years. Once it gets close enough, tidal forces will exceed the moon's structural strength, and Phobos will likely disintegrate, forming a ring around Mars, before the debris eventually falls to the surface. A long time from now, but relevant to the origin question. Working backwards from the current decay rate tells us something about where Phobos was in the past, and some analyses suggest it may have been further out, or not always in such a regular orbit. What emerges is a moon that's scientifically awkward in the best possible way. Its origin is contested. Its composition doesn't fit neatly into any single category. Its orbit is tidally clean, but physically doomed. Spacecraft from the Soviet Phobos program in the 1980s through to Mars Express and Mars Reconnaissance Orbiter have told us a great deal about it, and still haven't resolved the most fundamental question of where it came from. That's not a failure. That's science being honest about the limits of remote sensing and modeling, and building toward the next step, which in this case means getting a physical sample back to a laboratory on Earth. Easy to overlook, given its size. Phobos doesn't have the drama of Io's volcanoes, or the mystery of Europa's ocean, but in terms of what it could tell us about the early solar system, and the formation of the Mars system specifically, it punches well above its weight. Next time, we look at Phobos' fate and its exploration value. including why some researchers think it could serve as a staging post for future crewed missions to Mars. The full playlist is linked on the channel page if you want to follow this series from the start. And if you find this kind of measured, evidence-based space content useful, subscribing is the best way to make sure you don't miss the next episode. That is part 1 of Phobos. In part 2, we explore the next key question. Subscribe so you do not miss it.